Hello everybody, in this video we will discuss aldol addition reactions. I will be using a simple ketone and then we'll use that for aldol addition reactions. This reaction is very important in terms of biochemistry as well. So when you go over glycolysis chapters, you will see a similar version of this reactions and also many other metabolic process uses this strategy here as well. Okay, so let's begin here. So it's the similar idea that we have seen this over and over and over. So I'm gonna copy these structures, copy and paste. So I'm gonna copy paste the structure to show you here. So what happens? So this is our alpha carbon atom. So we have alpha carbon atom to the right and to the left. For simplicity, I'm just using to the right. It doesn't really matter. So that's our alpha carbon atoms. And obviously the hydrogen here is going to be our alpha hydrogen. So that is our alpha hydrogens. And if we use a strong enough base, a decent base, so let's say I'm going to be using OH minus because that's one of our ingredient, right? So what would happen? The OH minus will abstract the alpha hydrogens, and then you will, the two electrons, the two bonded electrons here will go back to the carbon atoms. So let's draw the product here. So we will make CH3, CO, CH2 minus. And what is the byproduct was? Byproduct was water. Okay, I'm gonna draw this here, plus water. So in a reaction that is in equilibrium, so if you remember from our Gen Chem, if a reaction is in equilibrium, reaction always favor the weaker acid. So a reaction always favor. So this idea is very vital to understand the aldol addition reactions, and also when we talk about cross aldol addition reactions later. So the reaction always favors the weaker acid. Okay, so in this case, I'm gonna assign. So on the left side, this is our acid, and this is our base. On the right side, this is our base, that's the one that is negative, and this is acting as an acid. Okay, so in this scenario, what you should do is you should find out all the pKa values of all the acid. So the pKa of that alpha hydrogen is roughly around 20. Okay, so we have seen this before. Again, pKa of alpha hydrogen varies between 17 to 20, 16 to 20, depending upon the group, but in general, 20. And pKa of water, we know that that's around 15.7, close to 15. So which one is weaker acid? Lower the pKa, higher the acidity, higher the pKa, lower the acidity. So this one here is a weaker acid. And based on our definitions, a reaction always favor the weaker acid. So you see the arrow, the equilibrium reactions here is going to be more biased to the left side than to the right side. So in simple term, so let's say I dumped 100 of these molecules, okay? Which means only a small percentage of those molecules will turn into negative. That's a critical idea because the difference is not that high. So here, let's say I dump 100 of these, okay? So a small percentage, I'm just gonna say maybe 5% change into this. So what does this mean? If I dump 100 of these, 5%, which means 5 of them will become this, and rest of the 95 will stay as it is, right? So this is again rough eyeballing number. So this idea that a small percentage will change into negative ions and rest of the stuff will stay as it is going to drive the next step of the reactions. So you notice what charge is this one? negative charge right there, right? So I'm going to draw it out. So in your mixture, in your reactions, you just made 5 of these, CH2 minus, CO, CH3. You just made 5 of this. What's going to happen is you still have 95 of these. So what happened? There is a negative charge here. And we know that carbon has delta positive, oxygen is delta negative. And what happened? Every time you have a negative charge and something electrophilic center, it's going to react with itself. So your reactions, it's going to react with itself because you still have 95 of this. Okay, so what's the product going to look like? I'm going to color code this so that you know exactly what did we do. So this is the newest bond we just made. And where it is connected to the pink carbonyl, CO minus, CH3, CH3. So again, this whole thing here is the same thing as here. Okay, O minus. So it's reacting with itself. So here's what would happen. So let's say you just made 5. Sorry, you had 5 of these. It's gonna react another 5 of this, and you're gonna make 5 of these. Okay, so you basically consume the 5 whatever you had here. So again, once you consume the 5, what happened? The equilibrium will be keep bringing them to equilibrium, right? So let's say you run out of this 5, because it's not gonna be stepwise, but I'm just giving you explanation. So now you had another 5 here. Now we got 90, and you just made 5 of this. So you see, you are slowly burning them out, right? So you're slowly using them out. So you're depleting from here, and you're making small percentage, and then you're keep using them to react with itself. So slowly over time, you're gonna find out maybe here 80. Eventually you have 80 of the, not eventually, then you have another 5, and then you just made 15 here as well. So slowly as you keep using, obviously half of them gonna react with itself. So you probably get 50 of these, right? So eventually you get 50 of these because it's reacting with itself divided by 2. Okay, excuse me, I'm sorry. Ooh, hopefully that wasn't loud. Okay, sorry about that, people. Okay, so we got water. So that's part of the reagent is OH minus, and water it's gonna neutralize. So basically it's gonna abstract. Again, it's all about equilibriums. So all the steps in this reactions are gonna be in equilibriums. So eventually it's gonna get neutralized, CH3CO, CH2, and next one is COH, CH3, CH3, and then you recreated the OH minus. So that's why OH minus is regenerated at the end of the reactions, and this OH minus would be utilized again. So the cycle continues. So even if the equilibrium is not, even if the first reaction is not 100%, very small percentage is going to change into negative, but slowly it will react with itself. Okay, so here is the problem. When you have two different things, so you cannot do this reaction. So you have to use only one ingredient. So let's say you have AH. So this is where the cross Aldol condensation reactions comes into play. So let's say you have a compound AH. So obviously you're gonna make A minus. Then A minus will react with another A to give you AA. Okay, so, but if you make a mixture of two different reactions in a beaker, so let's say you got A, H, and BH, and you try to do this reaction. So here's what would happen. In your beaker, you're gonna make A minus. You also gonna make B minus. Now A minus gonna react with itself, to make AA. A minus can also react with the B to give you AB. Same here, B minus can react with itself to give you BB. B minus can react with AH to give you BA. So you can get a 4 mixture of products if you try to cook 2 of them together. So practice this, how many possible different products. So which is you can get. So this is where the cross Aldol condensation reaction comes into play, which I will discuss in the next video. Okay, so that's all about aldol addition reactions. Oh, one thing I forgot to mention is this compound is called, so this is your carbonyl group. So this is your carbonyl group. We're going to call this carbon atom as alpha, the corresponding carbon atom as beta. Again, this one can also be called as alpha, by the way, but we are focusing on this OH group here. So this one is beta hydroxy ketone. Again, this is the class of compound. This is not the name of this compound. This is the class of compound which are very common in biochemistry. You will see a lot of these in metabolism chapter where you're going to have some sort of beta hydroxy compound involved. So keep those nomenclature, alpha, beta. This one would be gamma. So every time an aldol addition reaction happens, you can make this. So here is few things more for futures. Is if you have a beta hydroxy compound, you can actually dehydrate this to make alpha beta unsaturated compound. So here is something more. If you use heat and H plus, you can dehydrate, dehydration reactions, right? So dehydration reactions can make this CS3 CO CH2, and then you can create a double bond here, C CH3. Oh, by the way, this is going to be H CH3. So this is alpha beta unsaturated ketone. So when we deprotonate, so H plus, and you're gonna get water, by the way, the byproduct. So this is our aldol condensation reactions where you OH and a hydrogen from here is gone. So that's minus water. So you're gonna make a ketone. So this reaction you have already seen in our earlier chapter when we were studying dehydration of alcohol. Check back that mechanism, okay, how dehydration happens in acidic and heat conditions. Okay, so that's your aldol condensation reactions. So the product is here, aldol additions, and you can dehydrate to make this. So for general exam purposes, I will ask you to draw the aldol addition product in general. All right, let's stop here.